Thank you very much. Thank you for inviting me to give this talk, and thank you for this very nice introduction. I really been looking forward to give this talk. I hope you all can hear me. My voice is a bit affected by a previous cold, but I hope it will be okay. So the title of the talk is Molecular Machines and the EM algorithm. So the EM algorithm is a general algorithm that is used in statistics as a means to estimate parameters of a model. And molecular machines and nanoscale computing devices. I will introduce both of them later. This is just a brief headline. What I'm interested in here in this talk is in a specific class of models that are called hidden Markov models. And the EM algorithm for that class is called the Baum-Welch algorithm. It takes a particular nice form. Hidden Markov models, you might be familiar with those. They are statistical models, and they are widely used in bioinformatics and data science and elsewhere to capture an underlying hidden structure and data. For example, in bioinformatics or in genomics, it's used for genome annotation and frequency estimation and many different things. It's a very popular model and can be used in many different contexts. The aim of the talk is to design, at least design in principle, a molecular machine that performs the Baum-Welch algorithm. So that's my aim. And this is achieved by designing a reaction network, which in this context here is a dynamical system that implements the Baum-Welch algorithm, and then argue that the reaction network, at least in principle, could be implemented as a molecular machine. It's sort of a two-step procedure. We design a reaction network that implements the Baum-Welch algorithm, and then argue that this in principle could be implemented as a molecular machine. And it opens, of course, the possibility, at least in principle, it's a future thing, that molecular machines could perform statistical tasks. And that's really what we are after. So I should mention here at this point that this is joint work with some Indian guys, Abhinav Singh, who is now a PhD student in Dresden, Abhishek Behera, who is a PhD student at IIT Bombay, and Manoj Gopalakrishnan, who is a professor at IIT Bombay, but currently he's on sabbatical, I think, on leave, trying to make a startup company. So I will start by telling you a bit about molecular machines, then I will tell you about reaction networks, then I will tell you about hidden Markov models, and then I finally get to my aim of creating a reaction network that implements the Baum-Welch algorithm. So that's sort of the process over the next minutes. So molecular machines, a molecular machine or nanomachine is a molecular component that produces an output in response to an input. So there are many such examples, there are many natural examples. For example, cell replication could be seen as a molecular machine. One cell replicates and becomes two cells, or it could be something at a smaller scale or smaller size, perhaps just membrane pumps pumping some molecule from one side of the membrane to another side of the membrane. So in nature, you would find many such molecular machines. There are also artificial examples, and they are mainly found in synthetic biology or in some bioengineering, where new modules or devices or so are created or redesigned from previous or existing devices to achieve specific functions. That could, for example, be that you redesign a virus to get a new virus, or you redesign, you modify a gene to get a different gene product, and so on. So there would be many such artificial examples as well. You could also count among the artificial examples, you could also count the DNA computer that was built by Adelman in 1994 to solve the traveling salesman problem. I don't think the DNA computer really no, I should not go down that road, but that is another example, though an artificial example. In the past 20 years or so, there's been an increasing interest in trying to implement abstract dynamical systems with molecular machines. And that means that you would like to create a molecular machine that behaves in the same way as an abstract dynamical system. So, for example, calculates the same equilibrium state. In our case, the abstract dynamical system would be a reaction network. And this interest here is particularly fueled by potential applications in nanoengineering and nanotechnology. And it's sort of, there's some reason to this. It has been shown or demonstrated that formal reaction networks or abstract reaction networks can be compiled into a system of DNA strands, meaning actual physical DNA strands, by purely automated or theoretical means. And it has been demonstrated that these DNA strands, when after compiling, right, that these DNA strands, if you mix them in a test tube, implement the dynamics of the formal reaction network. So that means that if you have a reaction network with some dynamics, you can create a DNA strand system that when you put it in a test tube or whatever you prefer, actually will perform the dynamics of the reaction network. So that's an implementation of a reaction network or a dynamical system into a molecular machine. And this means, and this is important to us, this means that if an algorithm can be described by a reaction network, then it can equally well be carried out in a test tube by a DNA machine, because if an algorithm is described by the reaction network, we can compile it into a set of DNA strands, and these DNA strands, when put into a test tube, will do the same as the reaction network, meaning it will do the same as the algorithm. And that means that understanding how to describe algorithms in terms of reaction networks become a matter of interest. And just to give you one example, I have put one here, right? Here there's one species, N, and it says that 2 molecules of N form a dimer, become 1 molecule, and the dimer might degrade. So that's the molecule, that's the reaction network, and I claim that it actually computes the function N mod 2. And why is that? Well, if you start out with an equal number of N molecules, then they would all pair up and be degraded, and there would be none left, so there would be 0 left. If you start out with an odd number, then all of them would be paired up except for 1, because the last one cannot find any other one to pair with, and they will be left with 1. So in essence, it computes the N mod 2 function. And it has been shown, and it's an old result back from 91, that any Turing computable function could be computed by a reaction network in this way. So it means that reaction networks are actually quite powerful family of computers, if you like, right? But many other things has been computed by reaction networks too. I don't want to go into the specifics or into the details here. Just I have listed a number here: logical circuits, input-output system, Kalman filters, neural networks, and also some stochastic functions can be calculated by neural networks. No, sorry, by reaction networks. So that's, no, sorry, just to point to the application side, why we would like reaction networks on molecular machines to be able to perform statistical tasks. I have put this future application here, a little cartoon thing. So we might imagine molecular machines being used to learn an environment, for example, the environment in the body of a person, make a decision based on what it has learned, and take action accordingly. So you might imagine here a person here who suffers from stomach pain. He eats a molecular machine, that's the little blue one, that goes down his body, finds the desired location in the body. Then it learns the environment, so it means that it senses the presence of some molecules or the absence of some molecules or the concentration of something or combination of all of it, right? And based on what it learns, it takes appropriate action. So it releases some drug if something is present, it releases a different drug if something is absent, and so on, right? it might take a decision according to what it has learned, so it might take different decisions accordingly. So that's in contrast to standard medicine, right? You eat the same something that releases a drug independently of what is actually the environment. And a clever machine will, of course, use statistics to learn its environment. It will, of course, use a statistical model and optimization to learn the environment. So that means the little molecular machine should carry some implementation of a statistical model and some implementation of an optimization scheme with it when it goes down the body of the person. So that ends the first part on molecular machines, and I would now give a very brief introduction to reaction network theory, just so that we all on the same page and know the same thing, or the necessary thing to know. So this reaction network theory was probably formalized in the 60s and the 70s by Feinberg, Horn, and Jackson, but many others have contributed, and a lot of theory was already available before these three guys got into it. And in the past 10, 20 years or so, the availability of advanced experimental techniques and many new data types, the possibility to measure at the cellular level, has really fueled theoretical interest. And today we find a lot of different applications within genetics, epidemiology, systems, and synthetic biology in many different areas of biology. And what is interesting, but not particularly relevant for the talk here, but what I find interesting is that many different areas of mathematics has actually contributed to this development: linear algebra, dynamical system theory, graph theory, algebraic geometry, probability theory. Many different aspects of mathematics has gone into sort of this these advancements within reaction network theory we have experienced in the last 10, 20 years. I would introduce reaction networks just by example. So what you see here is a little example of reactions. So there's A plus B goes to 2A, and there's the reverse also, 2A goes to A plus B, and there are two other irreversible reactions. It's often useful to illustrate them as a graph instead, so you better see that 2A or A plus B actually is involved in several of the reactions. So this graph here is equivalent to this list of reactions. There are a number of species, A, B, and C. There are a number of complexes. The complexes are at the ends of the reactions. So A plus B is a complex, 2A is a complex, C is a complex, and we consider them as elements in non-negative integer vectors. So A plus B is, for example, the vector 1, 1, 0. Meaning there's one element A and there's one element B and there's 0 C's. And then reactions are arrows between complexes from one complex to another. So that gives sort of the reactions, but what we need in this context here is to make the reaction network into a dynamical system. So we need to know what is the speed by which these reactions occur. And what we would take here is mass action kinetics, or the law of mass action kinetics as the speed of the reaction. So this was introduced about 150 years ago now by two Norwegian scientists. And what they argued was that the rate of a reaction should be proportional to the concentrations of the participating molecules. So in the case we have a reaction A plus B goes to 2B, the rate would be the concentration of A times the concentration of B, so that is XA times XB, multiplied by some constant, here kappa 1, the reaction constant, reaction rate constant, and similarly for a reaction 2A goes to A plus B, the rate would be proportional to XA, the concentration of A squared, because there are two A molecules involved, and then there's a rate constant kappa 2. In this way, using that, we get a dynamical system by adding the contributions from each of the reactions. So here, the x dot A means the change of the derivative of the concentration of A over time, and similar for B and C. And what we get here is if we look at the first reaction, if A plus B goes to 2A, then we see that in this process, there's 1B being lost. We consume 1B. So we have a decline in the amount of B by the rate by which the reaction occurs. And similar, there's a gain of 1A in the reaction from A to 2A. So there's a gain in this case here comparable to the rate of the reaction. And similarly for the other reactions, I don't think I need to go into details with them. We can stop at the last one here that says that C is consumed, creating 2 molecules of A. So the rate by which the reaction occurs is concentration of C times the reaction rate constant. So the concentration of C goes down by that, while the concentration of A increases by 2 times that because 2 molecules of A are created. So in this way, we get a dynamical system. This is essentially what we need to know for this talk here. And just to end this part, I claimed that one could take a reaction network, a formal reaction network, and compile it into a system of DNA strands. And this system could be implemented in physically implemented. This is based on a paper by Soloveitch and collaborators in 2010. And I don't want to go into details. I just want to show that they can take an arbitrary chemical reaction, formal reaction, and convert it into actually a set of reactions between DNA strands that might bind based on DNA pairing or DNA complementarity principle. And they further showed that, for example, if they took a well-known system like the Lotka-Volterra system, you see at the bottom part in display A, and the corresponding DNA strand system is shown in B. It consists of more reactions than the original one, but they then showed by simulation that the dynamics is essentially the same. So the solid lines, the red and green solid lines here, are the concentration of the 2 different species in the Lotka-Volterra system in A. Over time, it shows oscillatory behavior. And the dashed lines are the same species in the DNA strand system. So you see after some time, there begin to be some discrepancies, but this only appear after some time. So essentially, the DNA strand system replicates the original reaction network. And this you can do for arbitrary reactions with arbitrary number of species and arbitrary number of arbitrary stoichiometric coefficients. So that was molecular machines, and it was reaction networks. And now I jump to hidden Markov models. And after that, we are sort of ready to move into the main part of, or the aim of my talk. Right? So my collaborators at IIT Bombay have previously described how one can estimate parameters in log linear models. Log linear models is also a very big class of statistical models used in many different contexts. They had shown how you can estimate these parameters using reaction networks. And this particular case is actually an instance of the EM algorithm but it requires an exponential number of reactions in the size of the model. And that's, of course, a very negative thing for implementing it in a molecular machine, because it means that the number of reactions explodes with the size of the model. Here, what I will describe to you is a reaction network that implements the Baum-Welch algorithm for hidden Markov models. And in contrast, the number of reactions here is linear in the size of the model. So it's more likely perhaps to possibly be implemented in a molecular machine. There are many examples in the literature of similar algorithms being implemented in reaction networks, for example, message passing, Kalman filters, and other types. I will not go into further details with that. But I will, to make sure we are on the same page, right, I need to tell you a bit about what hidden Markov models are. So a hidden Markov model is a statistical model of an observed sequence of L-dependent symbols, where L is some integer number. So what we observe is L-dependent symbols, V1 up to VL, where all the VIs are elements in some set V. For example, one could imagine a DNA sequence of length L, say length 100, with symbols A, C, G, or T. Or one could imagine a phosphorylation pattern on a protein, for example, L sod sites, protein phosphorylation sites, and the symbols being 0 or 1, meaning whether the site is phosphorylated or unphosphorylated. So you would have a string of 0 and 1s of size L. And the dependence, I mentioned that the symbols are potentially dependent. The dependence is modeled by an unobserved hidden sequence, which is assumed to be a Markov chain. And conditional on this hidden sequence, the observed symbols are independent random variables. So here one could think the hidden sequence, for example, could encode structural information about the DNA or the protein, or some other relevant molecular information. Here there's a little cartoon of a hidden Markov model with two hidden states, the two red ones, H1 and H2, and three visible states, A, B, and C, the yellow states. So the hidden state sequence would be generated according to a Markov model, for example, one of length 6, starting in H2, then one would jump to H1, H2, H1, H1, and so on. And one would jump with these probabilities that are given next to the arrows here. So whenever you are in state H1, you can either stay in H1 with some probability, or you can jump to the other state, H2, with some other probability. And the same goes for H2. When in a given state, say when in H1, you might emit a symbol, and you emit the different symbols with different probabilities. So the different probabilities are listed near the arrows, right? So you might emit A, B, or C, and similarly, if you're in state H2, you might emit A, B, or C. But these probabilities might differ depending on what state you are in. So here I have just written down the probability of this hidden state of length 6 I created, where pi here is the probability that you start out in H2, and then the theta probabilities are the probability of jumping or staying in a given state. So I would, throughout the talk, assume that the pi's are known. This is just a little technicality. And the theta, as we call the transmission probabilities. Oh yeah, sorry. And then on top of this, we have the observed sequence, and one could imagine the observed sequence was BCA, BCC. That would have given the hidden sequence we had on the previous slide. Then it would have this probability, just the product of the probabilities of emitting the different symbols from the different states. And these probabilities are called emission probabilities. Well, we don't observe the hidden states, that's why it's hidden. So to calculate the probability of an observed sequence, say here V1 up to VL, we need to sum over all possible hidden sequences and multiply by their probabilities. So that is what is stated here. There's a sum over all possible hidden states, and then the probability of the hidden sequences multiplied by emitting the respective symbols in the given states. So, and what we would like to be able to is, based on an observed sequence V1 up to VL, then estimate the parameters of the model. And one way of doing that is to use the, or even the standard way of doing that is to use the Baum-Welch algorithm. And it goes back to, I think, actually to the 40s, and maybe if not in the 50s. It's a very old algorithm that appeared in many different examples and got the name from Baum and Welch, who individually sketched a more general algorithm. The EM algorithm is iterative, so it's an iteration thing. You go through a number of steps iteratively, and each step consists of 4 subroutines. So one step in the algorithm is to go through 4 of these steps. So one iteration is to go through 4 steps: a forward algorithm, a backward algorithm, an E-step, and an M-step. And if you're not familiar with this or don't know what the forward, backward, E, and M refers to, I will not really help you on this, because I would just explain how the algorithm looked like and how we can make that into a network, a reaction network. But what is important is that at each iteration, an updated parameter value, here called theta n plus 1, psi n plus 1, is found based on the current value, theta n psi 1, psi n, that increases the likelihood. So we are at some point in space, right? We go through one iteration of the EM algorithm and we find a new set of parameters. And this new set of parameters has a property that the likelihood of the observed sequence has increased. At least it has not decreased. It might remain the same, but it does not decrease. So in this way, by iteratively finding new parameter values, we would get a sequence of parameter values that would increase the likelihood. Once the likelihood is not really increasing anymore, we might stop and report the parameter values we found at that point. And what is guaranteed is that if the parameter values we find in this way, iterative way, converges to some value, say theta star, psi star, then the likelihood value evaluated in this data, in this parameter point, is the local extremum of the likelihood. And local extremum means it can be a local maximum, or it could be a saddle point. It can even be a local minimum. If we start out in the minimum, we would remain in a minimum. So you're not guaranteed to find a global maximum in this way. And this convergence, you're neither guaranteed that there's a convergence, but this is often seen in practice. I will now briefly explain to you how the Baum-Welch algorithm works, but I will not go into too many details, because then we just drown in the details and don't get to where I want to go. I will focus here mainly on the forward algorithm. The forward algorithm has 2 steps, an initialization and a recursion. And so we introduce auxiliary variables here called alpha 1 and alpha L. And what we see is that they depend on the current parameter values, so psi and theta. And then it's the alphas are calculated in a recursive way. That means that alpha L depends on the current. Sorry, there's a lot of noise. There's a lot of noise now.
Sorry, I muted the person. It's okay now again.
Okay. Alpha L is calculated recursively based on the previous value of alpha, alpha L minus 1, and so on. So it depends on the previous, the current values of the parameters, and there's a recursive step here. And the same goes on for the backward algorithm. We introduce auxiliary variables called beta L, and they're calculated in a similar recursive way. Then there's an E step that also depends on the parameter values and the alphas and the betas. And then what I would dwell a little with is the M step. In the M step, we calculate new parameter or updated parameter values. So based on the current values, theta, comma psi, we calculate new parameter values, theta prime, comma psi prime. And these parameters has the property that the likelihood increases, or at least it does not decrease. We should just mention briefly, or I should mention briefly, that the observed sequence enter the algorithm down here. So this is the direct delta function, but just to make sure that we actually make use of the observed sequence, I point out that it is here. So here there's an algorithm, right? We can go through. We start with some value of theta and psi. We calculate new ones, theta prime and psi prime. We can take these values and plug into the algorithm again at the top of the slide, and then calculate new values again, and so we do recursively. So if we repeat application of this algorithm would yield a sequence we could index by n. This is pi here, it should say psi, and it says pi here, it should say psi. That's an error. So we get a sequence of parameter values starting from some initial value theta 0, comma psi 0. And the question I ask is, could this sequence be computed by a reaction network? If it could be computed by a reaction network, then we have found a way of calculating the Baum-Welch equilibrium or the Baum-Welch algorithm using a reaction network instead. So what we really ask is if each iteration can be computed by a reaction network. That means that we would have to iterate the reaction network also many times in order to replicate the Baum-Welch algorithm. Sorry. So to do that, I would focus on the forward algorithm and just explain how a little bit about the reasoning, how we get the reaction network without leaving out many of the details. So the forward algorithm looked like this. There was an initialization, and then there's a recursive step. And if you look at these two, this forward algorithm, you would see that it implies what we call the balance equations. So if you multiply alpha 1 h with alpha 1 h star, where h and h star are two hidden states, and use the definition of the alpha parameters, then you see that this equation holds. And similarly for alpha L plus 1, then you get a similar balance equation that holds here. So if you look at this one and this one, that prompted us to consider reactions of this form. So let me explain what this actually means. So now see, first of all, here on the previous slide, these are some quantities, right? These are parameters and quantities. Now I also use these parameters and quantities as names of species, not to introduce too many different symbols and too much notation. So here we take alpha 1 h as a species and pi h star as a species and so on. So in this way we get reactions, and 1 here indicates that we put the reaction rate to 1. So if we consider this little reaction system, so for each edge there's these reactions here, then we know first that only the red species, the alpha species, changes, right? The pi h star is the same on both sides, and the pi h here is the same on both sides, and the same goes for the psi species. So only the red species changes. So these two we would call for catalytic species in this context, because they don't change. They are only there sort of to facilitate the reaction to occur, but they don't change. If we write down the ODE system based on mass action that governs these two reactions, then we get an ODE system with components of this form here. So the change in the species alpha 1 h is given by the difference between these two here. And at equilibrium, that means when there's no change in the alpha 1 h, that is when this is 0, then we simply get this, and we see that is the balance equation. I can go back here, right? The balance equation was this one here. If we subtract one from the other, we simply get this. So imagine now that I fix the concentrations of the pi and the psi, so to the current values of pi and psi, and then I run this ODE system until equilibrium has been obtained. Since there's only, this is a variable and this is a variable, so this is a linear first order system, then I would eventually get to an equilibrium, and this equilibrium will fulfill the balance equation. What one can show is that this equilibrium is precisely the value of alpha 1 h in the Baum-Welch algorithm. So I take the current values of my parameters, I start the ODE system here from some arbitrary values of the alpha 1 h sequence, or alpha 1 h species, and then I let it run until equilibrium. And when that happens, then I have obtained that alpha 1h equals alpha 1h in the Baum-Welch algorithm. So now I have a little reaction network that actually does the first step of the Baum-Welch algorithm. I can replicate this for the other, for the recursive step of the forward algorithm. In this case, the reactions are more complicated. You note here that it also depends on alpha L plus 1, depends on alpha L, and then also the parameters. So if I first run the first step here until equilibrium, and then I plug in that value I obtain here, and then run the next one until equilibrium and continue in that way, then one can see that what we get is precisely the same as in the Baum-Welch algorithm. And since this essentially is a monomolecular or linear order one reaction network, we have linear equations, and we know everything about convergence and stability of the steady states of such a system. So that is what we can do for the forward algorithm. One can do something similar for the backward and for the E step and for the M step. It all amounts to things that where most of it appear as catalysts, so they are unchanged by the reaction. Only the red thing is changed by the reaction. So that means we only essentially need to study first order or linear ODE systems in order to check the convergence of the algorithm. So, or the network. I mentioned that one could start by running this until equilibrium, then running the next one until equilibrium for each value of L, and then do the same for beta and do the same here for each value of L and so on. So that means running things sequentially one by one. One could also imagine other ways of running this reaction network, right? One could take all of this together and just start with some arbitrarily fixing the parameters, because that's what the Baum-Welch do, right? You start with some current values of the parameters, and then we run the system with all the other variables dynamical, and then wait until equilibrium and see what happens. That would be a second system. And finally, one could essentially identify psi with psi prime and phi with phi prime, and then run it as one system. That means that phi would be continuously updated and psi would be continuously updated. So that gives three different ways of running this reaction network, and we are interested in knowing whether to what extent it does the same as the Baum-Welch algorithm. So here I have listed the three different ways of running it, called the BV1, where we run everything sequentially, starting from one end and then going through all of them. And then when we are done here, we update the parameter values, and then we rerun it again until we believe convergence has occurred. Or we could take all reactions in one go and run it until equilibrium, then update the parameters, rerun it again, update the parameters, and so on until we believe convergence has occurred. Or we could identify the theta species with the prime one and the psi with psi prime, and then run everything in one go. Then we don't need an iteration step because we update the parameters continuously as we go along. So that is sort of the ideal position to be in if we could do this, right? Because this would only require sort of to run a reaction network once and not iteratively. So here I've illustrated the BV2 versus the BV3. So BV2 is sort of an iterative approach, right? We start with some values of the parameters, then we run the system, we get a new value, we start the system at that value, we run the system and we get a new value and so on, and eventually we might converge to the blue dot. The BV3, where everything runs simultaneously, we might get something like this, and hopefully we would end in the same equilibrium. So what we know about the dynamics is the following, that the BV1, BW1, when initiated at the same point as the Baum-Welch algorithm, would actually produce the same equilibria as the Baum-Welch algorithm. So the BW1 actually does exactly the same as the Baum-Welch algorithm, but it's an iterative approach, right? We need to sort of restart things many times, and that might, of course, be difficult if you think of it being implemented in a molecular machine. BW1 and BW2 actually perform identically too. They produce the same equilibria. So running BW1 or BW2 or the Baum-Welch algorithm is one and the same thing. We can, in the BW2 case, we can even say that equilibrium is approached exponentially fast and is asymptotically stable. For the BW3, we know less, but what we can say is that the positive equilibria of the three different reaction networks are actually the same. So in principle, it's the same equilibria we can obtain, but we cannot say that when started at the same values, they would actually produce the same equilibria, because they might produce different equilibria, and that we have examples of. So I want to show you some example here before finishing up. So we are particularly interested in the BW3 because the BW1 and the BW2 actually perform the same way as the Baum-Welch algorithm. So we simulated a sequence of length 100, and you might think 100 is very little, but when you get this into the number of reactions, right, you get many reactions, something to the hundreds of reactions, because the number of reactions scale in the length of L, or in the size of L. So we generated a sequence of length 100 with 2 hidden states and 2 visible states. So that's sort of the smallest hidden Markov model we can imagine, but with a somewhat large length. And then we run the 2 algorithms, BW3 and the standard Baum-Welch algorithm, for different choices of initial values, and saw what equilibrium value we obtained. And in the first case, we find that they converge to the same points, but these are actually far from the true values we used for the simulation, but that's another aspect we don't need to be concerned with now. But they returned the same equilibrium value, so they agree in this case. But we also observed that in cases they did not agree, and they could actually return very markedly different values. And in the second case, for the Baum-Welch algorithm, we obtained these values put up here, whereas for the BW3, we obtained some values that was, sorry about that, that was at the boundary. So in this case, they are quite different, right? You also see that the likelihood values differ, but not by much. This has a slightly better likelihood value than the parameter values returned by BW3. You might see in the log likelihood that might be of interest. You see over time, this is for BW3. In the first case, you see that the likelihood is actually increasing. We are not guaranteed that to be the case, but we sort of conjecture that that would be the case. And it's the same for in the second case. It has a steeper increase in the beginning, and then it slows down, but it's still increasing. And the Baum-Welch algorithm also has an increase in the likelihood, but that is known, right? That is known that in each iteration of the Baum-Welch algorithm, the log likelihood is actually increasing. But you see that the two curves are actually quite similar. So we hypothesize that there might be some connections between the dynamics of the BW3 and the log likelihood, but we have not been able to sort of get anything more detailed out of that conjecture. So some applications, just to round off. Some promising areas of application might come from cellular biology, right? many cellular processes, partial information about the environment is available in form of a sequence of observations. And this might, for example, happen, as I mentioned earlier, if an enzyme acts on a substrate or a molecular walker locates a position on a grid. So one could imagine many examples where this would actually fit into. And as already mentioned in my little cartoon, right, one might in the future imagine a molecule-based hidden Markov model implemented as a molecular machine would learn the environment in an organism and take action accordingly after it. So this should be the summary. I put the title application here. It should be summary. So what we have accomplished here is a step-by-step reaction network implementation of the Baum-Welch algorithm that performs precisely as the Baum-Welch algorithm. However, being step-by-step means that it would be difficult to implement as a molecular machine in a cellular environment, because you would need it sort of to be able to restart itself after each iteration, and that might be very hard. Alternatively, we propose an all-at-once reaction network implementation that actually has the same equilibrium as the Baum-Welch algorithm, but not the identical behavior. So it might return equilibria different from the Baum-Welch algorithm, but they would nonetheless all be the same positive equilibrium points. And it has the advantage that it's sort of a thing you only have to do once, and you don't have to iterate it. There are things we are thinking about, we would like to work on in the future. For example, what goes on in a cell is essentially stochastic, because the number of molecules is small. So some of this should not be seen in the deterministic perspective if we want to implement it into a molecular machine, but in a stochastic perspective, and that makes things a little harder, or to say it mildly, it makes it a lot harder. At least we have not been able to see the way through yet. And then, of course, there's one would like to have simplified reaction networks with fewer reactions, fewer species, something that is simpler than what I have presented here. But this is also for the left for the future. With this, I would like to thank everybody for listening.